Hello. We, Aamir, Krishna, Raghav, Saksham, Samaksh, working under the guidance of Dr. Anuj Grover, welcome you to our presentation on Simulink model for in-memory compute platform.
Hi Raghav. Have you noticed how the world has been taken away by artificial intelligence and machine learning?
Yes, Samaksh. AI has been introduced in problems like classifying images on Google Photos, health monitoring, designing game engines, self-driving cars, and a lot more.
The other day, I tried to run a neural network on my laptop to recognize handwritten digits, and it took forever for the network to finish its training. On top of that, the battery consumption was immense.
Your observation is correct. Due to the von-Neumann bottleneck, we are facing critical performance and power limitations. Moreover, the computation behind training a neural network is exceptionally data intensive.
Let's understand what this von-Neumann bottleneck and von-Neumann architecture really is. We know that the ALU is separated from the memory. So if we need to compute A plus B equals C, we need to access the memory multiple times. First, we need to bring in A from memory. Then we need to bring B from memory. And after we have done the computation and figured out what C is, we need to send this data C back into the memory. You can understand the number of times you need to access a memory for a single addition. Now imagine what would happen in case of a matrix multiplication, which is the heart of a forward pass of a neural network.
A lot of a lot of research has been gone into solving this issue, and engineers and researchers have tried to bring the ALU closer to the memory to improve performance and power consumption. However, wouldn't it be ideal if we could compute inside the memory itself? We wouldn't have to access the memory again and again for the data. The result could be calculated within the memory and then stored at the appropriate address.
Considering the requirement for in-memory compute, we are working towards building Simulink models that could estimate the PPA, power performance area, of different models the designers would create to perform IMC. This would minimize the effort of the designers to iterate over multiple possibilities, and they would be able to come up with more robust designs much faster.
So the question that arises here is, why is there a need for a Simulink model? So in a memory, there are multiple components such as the decoders, sense amplifiers, write drivers, and also the memory bit cell, which can be a 60, 80, or any other type of cell. So this provides a designer with numerous design types and multiple IMC architectures to choose from. And this makes it difficult to choose an optimal design which meets all the requirements. So the main aim is to get a quick and accurate estimate about the power, performance, and area for these different implementations. So a Simulink in-memory compute model will provide the designer with a faster design space for exploration due to the overall reduced complexity for simulation with the low computation times. And it will also be able to compare multiple designs for PP analysis quickly to give an estimate, which will in turn reduce the overall design effort and save a lot of time.
So in this project, we model each and every component of memory array using Simulink blocks. So firstly, row decoders are modeled in two stages. First are the pre-decoders. In a model, the designer determines the number of pre-decoders used in the circuit. So here in this Simulink block, we support 4 different types of predecs. Next, based on the number of pre-decoders used in the circuit, the number of post decoders are determined by this post row deck block. And in this block, the designer needs to specify the type of post deck, the word line capacitance, and the word line on duration. Based on these parameters, the post row decoder power consumption and the pre row deck power consumption are calculated. Also, each and every block has its own power consumption characterized and stored in that. Next, similarly, in the column decoder part, based on how many ADCs and sense amplifier are required, the power consumption of these column decoders are calculated, and each of the ADC and sense amplifier are pre-characterized, and the power consumption for that is stored in this ADC and sense amp blocks. Finally, the bitcell array is so the Simulink model for memory array emulates the read, write, and in-memory compute operations of data. Here we model 60 bit cells and by using the current and the voltage valve equation. And based on the different input parameters like the read enable, read row, and the write enable, and all these other signals, we estimate the power consumption the power consumption in the bit line discharge for the different scenarios like the read operation, write operation, or the in-memory compute operation. So yeah, so in future we are working on improving the robustness of the Simulink this simulator by implementing multiple blocks. Also, we expect that different kind of IMC architectures can be simulated using these Simulink models. So, and finally, even if a technology is not ready for fabrication, designer can still evaluate the power consumption gains in a circuit if he used a certain kind of technology, even if the fab is not able to provide the PDK file for that.